Hello everyone. Today my talk is about RWKV-7, the next generation model architecture. And I'm from Shenzhen University, and I am one of the author of the RWKV-7 papers. So I'm happy to introduce our work to you. Okay, first is our some new models I want to announce. The Raku G1 reasoning model. Some Japanese friends test our Raku GE model in Japanese and I get a very good result. Here is a result for English reasoning. This is our demo space. Yeah, you can go to Hugging Face to use this demo. And Raku is a sequence model, so actually it can be used in so many areas, like language models, vision models, say 3D and 4D models, RL models, and audio models. Yeah, so you can visit our website to see the Raku related papers. Okay, this is a demo for Raku to play Sukudo. Yeah, you can see actually Raku can solve any solvable Sukudo with a very small model size, just 12 million parameters. And it can do in-context learning. Raku learns reasoning from data, and it can generalize from 8K, which is the training context, to 4 million. Yeah, so testing the COT without any errors. And very important one is Raku is RNN, so as an RNN, speed and VRAM use are constant and regardless of COT length. So it's very suitable for Raku to run a very long COT. Okay, here this case is for Raku to play Othello. Yeah, Othello. We just use a 10 layers Raku 7 and with a very small hidden dimension with 256 8.8 million parameters. And we found by control thinking budget via alpha beta pruning with width and depth, actually Raku 7 can outperform the baseline with a higher budget. This demonstrates positive test time scaling through better strategy search. Let's begin by looking at the limitation of traditional RNN and transformers. First, RNN has the vanish gradient problems, so which make learning long-term dependency very difficult. And RNN, we know it processes step by step and only can handle one character or a word at a time. So this limits its scalability. On the other hand, transformer has the quadratic time and space complexity problem, resulting in high computational cost and memory usage. So to address these issues, we announced Raku. Raku was introduced as a new generation of RNN. Actually, Raku can be trained in parallel and very strong scalability. And the time and space complexity of Raku during training is O(n), and the time and space complexity of Raku during inference is O(1). So this makes it highly efficient and suitable for deployment on source constrained device. What's more, let's talk about the limitation of transformer and member. Actually, recent theoretical paper has shown that transformer and a state space model like member are unable to solve problems that essentially require sequential processing. So these models, transformer and state space model, can only recognize language belong to the TC0 class, which is a category of computational complexity, and cannot express problems that are complete for NC1. Yeah, we can see this figure here. And Martin Yu has proven that the chain of thought needs to be long enough for a transformer to solve the problem belongs to the NC1 class. So, and furthermore, that paper say RNN with a diagonal transition matrix can only present function and problem belongs to TC0 class. So we want to go beyond the limitation of NC0 TC0 constraint. So we think, okay, how to do this? And here is our RWKV-7's philosophy. RWKV-7 derivative from the first principles. The internal state of the model must continuously fit the external world. What does this mean? Let's recall the QKV softmax attention. We have some key and values K0, V0, K1, V1, and we have a query Q. So if the Q equal Ki, actually we will get the result close to Vi. If we have the Q is close to the average of Ka and Kb, and we will get the result close to the Va and Vb. So RWKV-7, we think we just want to dynamically train a model that can mapping Ki to Vi using the in-context gradient descent. So by this way, if Q equal Ki, the result is close to Vi. If the Q is equal to the average of Ka and Kb, the result is close to Va and Vb. That's amazing, right? So here we propose the RWKV-7 core formula. So okay, I will explain the principle of RWKV-7 as a meta in context linear. Given two sequence of Kt and Vt, RWKV-7 will test time train an internal model, which is V is equal to Ks via in-context gradient descent. So we use the L2 loss, so which is this one, right? So we can get the gradient of L2 loss is this formula, and we use the gradient descent formula with the weight decay Wt and the learning rate neta t, and finally, and then we will get the update form equation for our RWKV-7. You can see this term actually is okay here. This term is our gradient, right? And we times and then times with the learning rate to control the step of each update. And here we have st minus 1 and the weight decay. Actually, by this way, we will remove some knowledge, some information from state every time, and which we can rearrange this formula and we can get this equation. And this is our core formula for RWKV-7. The first term you can see is how we remove information from the state. The second term is how we add new information to our state. And we can also get a general formula, which is this one. Okay. So, and we found RWKV-7 can enhance long-term memory by continuously fitting the external world. And we use a non-diagonal transition matrix. So RWKV-7 can go beyond the TC0 constraints. Okay, one sentence to conclude. RWKV-7 use KT-VT to test time train an internal model and use RT as the input for this model. It overcomes the TC0 limitation of QKV softmax attention transformers, while still being effectively trainable on GPUs. Such idea can be traced back to fast wait, delta rule, and long ago. So let's see the procedural code. Actually, the procedural code shows how the internal model is updated over time with AT, BT, KT, and VT. and how to compute the output from state and RT. Okay. And we think RWKV is an architectural paradigm, a new architectural paradigm. Actually, the origin of the name RWKV is from receptance, value, weighted, and key. So WKV is the paradigm distinct from QKV. Here is the overall architecture of RWKV-7. Actually, RWKV-7 is a GPT-like architecture. We have time mixing and also have channel mixing. And here is how the time mix perform. First, we will do token shift, then we will do weight preparation, and all the weight will go into the RWKV-7 kernel, and we use a matrix to read out our information from the state or the internal model. So the WKT state also will be updated in the kernel. Okay, so this slide shows how to do the token shift and the weight preparation. First, the token shift combine each token with its previous token, and we use the data independent linear interpolation for the token shift. And this is from RWKV-5. And we don't use the data dependent linear interpolation because it will slow down our training process. And for RWKV-7, the weight preparation is doing as this way. We use a LoRa MLP structure. Each input will multiplied by two matrices, A and B, and will have a bias, lambda. So we can say, like the alpha t, the in-context learning rate will be prepared this way. And other all parameters will have its own preparation formula. If you are interested in this part, you can go to the paper, and we have a lot of discussion about how we do the weight preparation. This slide shows how time mixing in RWKV evolved from RWKV-5 to RWKV-7. RWKV-5 uses a learnable channel-wise mixing. The weights are learnable but not time-dependent. They don't adopt over time. So in RWKV-7, we introduce a channel-wise weight decay over time. It's a time-dependent channel-wise weight, WT. And this gives the model more control over how much it remembers at each time. In RWKV-7, we introduce a new diagonal plus low-rank dynamic evolution mechanism, or we can also say it's a structured low-rank gating. This enables a fully dynamic control content while memory mechanism. RWKV-7 introduced low-rank gates that adaptively control memory decay, enabling much more expressive and dynamic low-range modeling. So in summary, RWKV-5 learned a fixed mixing, RWKV-6 learned it time-aware, and RWKV-7 turned it into a dynamic and adaptive memory system, paving the way for strong LM performance. In this slide, we will compare the core formula of time mixing in 4 dimensions. The first dimension is large state. If a model has a large state, in this slide, we will compare the core formula of time mixing in 4 dimensions. The first dimension is large state. The state is the matrix shaped, or it has a 4 times larger than the model dimension. We call it a large state. Only RWKV-4 don't have a large state. The second dimension is flexible decay, which means the decay term has a dimension larger than the model dimension. And the third dimension is dynamic dependence. Decay vector or decay term WT depends on the input XT. The fourth dimension is generalized eigenvalue, which means evolution matrix allows eigenvalue beyond 0 to 1. RWKV-7 extends the data update rule into a more expressive form. We are retaining a diagonal plus rank 1 structure enable efficient parallel training. And this slide shows the computational cost analysis. And here is how to count RWKV's parameters. We have embedding, output, and weights. We have per layer parameters, and we will exclude the value residue from the low rank MLP. Normally, the inference flows are 2 times of the parameters plus 6 times of WKV computations. And the training flows normally are 3 times inference flows. And what I want to focus or highlight in this slide is the internal state size. And at the beginning, the internal state size of RWKV-4 are very small, only 5 DL. And in RWKV-6 and RWKV-7, we have 16.6 DL state size, which is 10 times larger than RWKV-4. And the KV cache size of a transformer is 2 DLT, which T is the sequence length. This means RWKV-7's state size is highly compact, equivalent just to 33 tokens of a transformer KV cache. In this slide, we show the result of RWKV-7 on language model benchmarks. Here is on English task. This slide is on multilingual task. And this is the full table. RWKV-7 shows competitive result across benchmarks. And this is a long-term test evaluation. And we can see RWKV-7 is better than RWKV-6, better than RWKV-4, or RWKV-5 and RWKV-4, which show our model has stronger and stronger long contest ability. And we also compare with member, and we found RWKV-7 is much better than member 2 and member 1. And we can see here the member 1 loss explode after maybe only 4K. After 4K, the member 1 PPL is explode. In this slide, we show the result of needle in a haystack evaluation on RWKV-7. RWKV-7 1.5B model trained on 4K tokens can retrieve perfectly up to 90K tokens, and for 2.9B model can perfectly retrieve up to 35K tokens. And we also do some continuous pre-training on 120K token data, and the 1.5B can be further improved to 29K tokens, and the 2.9B model can be perfect retrieve up to 30K tokens. But we are not satisfied with this result, so we have a new work. I have a new work. Name is the RWKV-X. We introduce the sparse attention and hybrid with the RWKV-7 model, and we achieve perfectly result on the needle in the haystack evaluation up to 64K contest. So if you are interested in that work, you can search, and we already pre-print it. And here is the speed performance, and we can say the RWKV-7 outperforms flash attention with V3 in speed when the contest length exceeds 4K. And here is some result from the visual language model. First is the visual language model is visual RWKV-5. This model is only a section of the RWKV-5 paper, and we use data independent recurrence, image first prompt, and unidirectional scanning. and the result is just so-so. And then we improve our model. First, we use a data-dependent recurrence, and it's improved 10 points on the VQA benchmark. And then we think the image are two-dimensional information, so only one-dimensional scanning is not enough. So we propose a bidirectional scanning and improve our model a lot. Finally, we use a sandwich prompt, which means we put the image at like a sandwich. We put the prompt first, and we put the prompt last. So by this way, we can improve our model. Finally, the Visual Roku 6 achieve a comparable result with the Lava 1.5, but still with a better efficiency. And we also test Roku 7 using the Visual Roku 7. And here all settings kept consistent except for Roku block to ensure fair comparison. And we can see the Visual Roku 7 only use 1.4b parameters can outperform Visual Roku 6 on VQA and GQA. And on SQA, it's an out of domain benchmark. 2.9b version exists 3.1b Roku 6. It means it has a better out of domain generalization performance. And on TQA, Roku 7 improved 5.3 points over Roku 6, confirming it has a stronger associated recall ability. Okay, another experiment is the group state tracking. What is the state tracking? You can think like this way. Here we have a vector, and we will swap x2 with x3, and we will track the final state after multiple swaps. And the Roku 7 can solve this with just 2 layers. And this paper also proved 4 layers Roku 7 can simulate any DFA. But fixed depth transformer cannot handle this task without COT. Aiding COT increase context length, and it will lead to quadratic cost and limiting scalability. So Roku 7 exceed classic transformers in expressive power and efficiency. And we also do a visualization of the WKV state matrix to better understand our inner model. First, we measure the RMS of our matrix element, and we found actually Roku 7 has a very low range of the value. But for Roku 6, you can see so many outliers here. The range is very large, and the numerical stability of Roku 6 is not as good as Roku 7. Then we use stable rank to measure the effective information content in the state. And we found very interesting thing. Actually, after context length increase, the stable rank of Roku 7 goes down. This is not, in our opinion, is very strange at the beginning, but we think because we have a better mechanism, so in our inner model, we don't have to store so many information because we can reconstruct it better. So here we have a lower stable rank for Roku 7. Okay, that's all. Here is the takeaway. Roku 7 offers a better trade-off between performance and efficiency than the Ethernet, T10s, and TTT. The architecture is still evolving. Innovation continues. As tasks grow more complex, full attention model hits limits. Hybrid and novel structures like linear attention RNNs are gaining traction. Future AGI models will need to run code, access memory, and handle long context. This area is a RNN and the linear architecture has a natural strength. The shift is clear. We are building not just brain but intelligent system with tools. Okay, thank you for your listening. This is my talk today. If you are interested in our work, very happy to we are glad that you can join our community. You can join our Discord, and here is my email and my homepage. Thank you a lot. Thank you for listening again. Okay,